Newton's comprehension of gravity, sufficient to propel us to the moon, forever feels like we've gone back in time, wondering if we get what it is. Newton's discovery is more than just a concept. It is a key that could shed light on the mysteries of the universe, demonstrating to us how the universe works wilder than anticipated. How does Brian Cox's new idea about time disrupt our thinking, and what could it mean for how we perceive things? It follows us as we check out Brian Cox's brand new, inspiring idea about what time is and the huge puzzles abounding in the cosmos all around us, waiting to be solved. A lot have to rely heavily on gravity and time in our lives. Imagine a world in which time acts weird, can slow down or speed up. Additionally, the force that keeps us on the ground might not be what we believe it is. This is where Albert Einstein's relativity theories come in. They give Einstein's new perspective on time and gravity. A well-known name gave us a new way to examine the universe using his theory of relativity. His work helped us get how time acts in different situations. Like when things move super fast, it all started in the early 1900s, when Einstein shared two major concepts: special and general relativity. Special relativity, from 1905, changed how we see space and time simply because it says the rules of physics are the same for anyone who isn't accelerating, regardless of how they're moving. This concept raises things like slowing or stretching time down under some conditions. A cool experiment to illustrate time change is the light clock. Imagine you're in a spaceship going super fast, close to the speed of light. There is a light beam bouncing between two mirrors within. According to physics, light speed does not change for everybody. So the light seems to follow a path with a greater angle for someone outside. The light's travel time on the ship traveling along this route ought to be the same for both inside and outside people. But since the path is longer for those who are outside, it looks like it takes the light longer to finish its trip. This time difference is what Einstein called time change. Time goes slower for the person moving compared to the one standing still. So time acts differently based on your speed. Knowing how things change when they move fast, or relativistic effects, isn't just an idea. Scientists make use of large machines like the Large Hadron Collider to push particles traveling at the speed of light. Because of how quickly things move, we must think about time in a unique way to obtain correct predictions and measurements. In addition to Einstein, special relativity in 1905 changed the way we get the universe is mostly about movement and time. This idea goes against what we might think. It says physics rules are the same for everyone, even if they're not still. This is different from what we feel every day, where we think if something is moving and we increase its speed, it just accelerates. But Einstein states there's a top speed, the speed of light. With this in mind, things that look like they happen at the same time for us may not appear that way to others moving at the speed of light. Another resulting concept is length becoming shorter. This has some significance. It looks shorter in the direction it's moving when viewed from a still location. There's the famous equation E equals mc, demonstrating how mass and energy can affect each other. This is key for seeing how tiny particles, when they move quickly, elucidate topics like nuclear reactions. In real life, special relativity is more than just a thought. We depend on it in tech, like GPS. When your GPS device receives signals from satellites, they are moving, and as a result, time runs a bit differently for them. If we didn't think about how GPS tracks time, the math would give you inaccurate location data. So special relativity teaches us time varies from person to person, depending on how things are moving. This messes with how we see space and time most of the time. Our usual conception of the universe is somewhat wrong. Time is not established. It is altered by movement. Some fundamental concepts like light speed being steady and how energy and mass connect have been demonstrated numerous times. However, the additional general relativity of 1915 delves deeper into how the structure of the universe and gravity interact. It changes the usual idea of gravity as nothing more than a pull force on things. Instead, it says gravity comes about because space and time are bent or curved. This is analogous to claiming that gravity is not an unseen force. It's just how things move in the universe. Per Brian, general relativity requires consideration of the universe as four parts: 3 space, and 1 time. Gigantic objects like stars, planets, and even us bend space and time around them. We experience this bend as gravity. Imagine space-time as a big, stretchy sheet. Something heavy like Earth is on it, it makes a dip. You put something smaller, like a ball, near Earth, it rolls over the dip, just like things move because of gravity, not because of a force, despite the fact that space-time bends. General relativity explains how planets move around our solar system, circling the sun. It can guess the paths these planets take, like how Earth makes a circle around the sun. This is different from the old idea of gravity simply bringing things together in a manner that could not adequately explain planets. The new idea is that time and space are bent like a bendy fabric, which fits better with what we see. A big event showing general relativity was right happened during a 1919 solar eclipse. Sir Arthur Eddington led a group to observe how light from far stars bent as it passed the sun. According to the theory, the sun's weight would curve the starlight a bit. The observations proved Einstein was right, showing the theory was good. Just like movement can alter our perception of time, gravity affects time too. Where gravity is strong, time goes slower than where it's weak. So, if you were standing close to a bulky object, like a black hole, your clock would slow down compared to one far away from the heavy weight. General relativity brings up black hole spots, where gravity is so strong, even light can't get through. The edge of a black hole is called the event horizon, and it's where there's no going back. Once something touches this edge, it pulls into the black hole forever. Einstein's general relativity has a significant impact on the structure of the universe. He first added a concept known as the cosmological constant to his equations because he thought the universe did not change. But when he found out the universe is growing, he called this a major error. A universe that is crucial to the Big Bang theory, which explains how the universe started. Another big idea of general relativity is gravitational waves. These are bends in space and time caused by heavy things moving quickly, similar to how black holes join. In 2015, scientists at LIGO spotted gravitational waves supporting Einstein's theory. Over time, scientists have conducted tests to verify general relativity, and it's always been right. Watching planets, light bending, or recognizing gravitational waves, general relativity is still a sound and good idea. Saying gravity is a myth might sound wild since we feel it every day. But in physics, it's common to ask and think back to previous hypotheses. Brian frequently wonders about common concepts in gravity. Some people have new theories, like enowned, or modified Newtonian dynamics, saying gravity acts differently at low speeds, mostly in galaxies without dark matter. Instead of unseen matter, enowned says at slower speeds, gravity becomes stronger. There is also talk about dark matter and dark energy, added to explain things in space. Some suggest that these ideas may not be necessary, and other ideas may be able to explain what we check out. A few scientists who don't follow Einstein's gravity look into new stuff, such as theories involving unknown particles or forces that have the potential to alter gravity. It's good to know that new ideas emerge in science. They aren't just thrown out. They're tested to examine whether they endure. For instance, Einstein's idea of time as a 4-part thing that prevents time travel by light speed has been looked at with ideas like Stephen Hawking's wormholes. Protection of the chronology enables time travel into the past, impossible in physics. To determine whether these new theories can explain gravity in a way that fits what we know. Many known ideas have not really been replaced by new rules of gravity. Questioning ideas is crucial for science's development and improvement of our comprehension of the universe through gravity. The theories of general relativity continue to be most important. Even with new ideas, it carries on doing well and explains things like planets and light bending. General relativity lasts because it's simple and corresponds to many of Einstein's unique relativity ideas. Saying time can change based on your speed. Let's see how this hits real life, mostly in space. Moving in space is fun, but difficult due to the vastness of space. Speed is the most rapid, so switching between stars is difficult, even with superior technology. To learn how time flies when you move in space, think about the twin thing. One remains on Earth, while the other moves to a fast trip to a far star. When the space twin returns, They discover they have aged slower than the twin on Earth. Planets on Earth move into the future. Time is big for space travelers. The more time spent traveling, the slower time changes. If astronauts move too close to stars, they would age where time moves quickly, slower than the human race as a whole. It sounds like a story, but it's real. Imagine sending people to a distant star. Even if they move quickly, the trip could take years. The astronauts would sense a slowing of time because of the passage of time. From Earth, more time would pass before the moment arrives. Technology, as well as computers and communication ships, have to think about time change to work effectively. Space movement has body problems like being alone, getting hit by space waves, and being far from Earth for a long time in daily life. We see time change in GPS. GPS needs right signal times from satellites because when satellites move, they experience time differently. Consequently, it is essential to include it in the calculations for accurate readings, without thinking regarding how a change in time would affect driving. Now, why do we only go one way in time? Our lives are governed by time, going back in. Time to the future and now. This one-way trip is part of us. But why? To get this, we look at the mechanics of entropy. Entropy, tied to time's direction, tends to grow as time goes, pushing time to go one way. According to the second law of thermodynamics, in a closed space, entropy will either increase or decrease. Entropy thrives in it, never falls on its own. Due to the nature of time, deeper exploration, time, as we perceive it, is intricately linked to the idea of entropy. The fundamental principle in thermodynamics determines the amount of the second law of systems disorder. The theory of thermodynamics says that in an isolated system, entropy tends to increase over time, leading to a transition from normal to abnormal. This principle not only governs the behavior of actual systems, but also offers a structure for comprehending the unidirectional flow of time. To illustrate this, consider the analogy of a castle made of sand. A castle made of sand represents a low entropy state, distinguished by a high level of order and structure. Over time, as a result of erosion and wind, natural forces, the sand castle will become nothing more than a pile of sand, a state of higher entropy. This transition is an example of the natural inclination of systems to progress in greater disorder, reinforcing the concept that time flows in one direction from past to present, learning about gravity, and the space-time fabric that grows. Upon the general relativity theory proposed by Einstein, gravity is more than just a force. It's a symptom of the shape's curvature of space-time caused by mass and energy. Massive objects like stars and planets alter the fabric of space-time, and this curvature dictates the motion of objects, including light. This revolutionary perspective altered our comprehension from viewing gravity. It's a force acting far from being able to identify it as the result of space-time geometry. A powerful illustration of this idea is the observation of gravitational lensing, where light from distant stars sways around bulky objects like galaxies. The reason for this bending is that space-time is curved by the galaxy's mass through which the light moves, changing its path. Such phenomena provide tangible evidence of the active interaction between mass, energy, and the structure of singular space-time. Among the most intriguing general relativity predictions are black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. The fundamentals of a black hole is the point of singularity, where the space-time curvature becomes infinite and our current understanding of physics breaks down. The event horizon defines the limit beyond which nothing can reappear, rendering black holes enigmatic and captivating subjects of study. The most recent developments in observational equipment, like the Event Horizon Telescope, have enabled scientists to capture images of black hole event horizons, providing empirical supporting data for theoretical models. Not only do these observations confirm aspects of the theory of general relativity, but they also open new avenues for exploring the fundamental nature of space-time and gravity, the concept of time. Travel has long been a topic of interest and speculation within the overall context of relativity. Specific approaches to the results of Einstein's field equations suggest the theoretical possibility of closed time-like curves that meander through space, looping back on themselves, potentially allowing for time travel to the past. However, these solutions often involve exotic conditions, such as the presence of negative energy or imagined physicist constructs like wormholes. Stephen Hawking proposed the chronology protection theory, suggesting that the laws of physics may prevent time travel to avoid paradoxes and inconsistencies, while time dilation, a relativistic effect in the passage of time at various rates for viewers in relative motion, is experimentally verified and has practical applications. The traversal of time in a manner akin to science fiction remains speculative and unproven. Latest news and breaking headlines: the significance of math in understanding the universe. Mathematics serves as the communication medium through which nature's laws are expressed and understood. Physicist Brian Cox focuses on the lessons that our experiences teach us, that there are indeed laws of nature, behaviors that are routine in nature, and that the best way to express these laws is using the language of mathematics. This perspective underscores the profound relationship between mathematical structures and the universe's physical makeup, highlighting the ability to predict mathematical representations for describing natural phenomena. The creation of mathematical structures, such as tensor calculus and general relativity, has been instrumental in formulating theories that accurately explain the way gravitational fields and spacetime's curvature work. These mathematical tools enable physicists to make accurate forecasts and get a better understanding of the expansion of the cosmos workings. Galaxies in the distance can be observed, showing that the universe is expanding, with galaxies moving away from us at speeds proportional to their distance, a phenomenon described in Hubble's law. This expansion suggests that the universe had a singular origin, commonly referred to as the Big Bang, and has been evolving ever since. The discovery of the cosmic microwave background radiation provides further evidence of the universe's hot and dense beginnings, offering a snapshot of the early universe and helping to explain the Big Bang model. Understanding the expansion of the universe not only reveals its origins, but also lays the groundwork for our knowledge of cosmic evolution and the universe's ultimate fate. In conclusion, the interdependence of time, gravity, and the universes. Exploration reveals a universe that is much more complex and interconnected than our everyday experiences suggest. From the curvature of spacetime controlling the movements of planets to the enigmatic nature of black holes, these concepts challenge our perceptions and inspire deeper inquiry. As scientific understanding improves, the interaction between the cosmos, time, and gravity continues to captivate and expand our knowledge of the universe's fundamental workings. Seeing how things go through a mess helps us see things in one way, like stirring or melting ice.